Hello. In this video, we'll discuss functions. We'll give a brief introduction to functions and function notation. And then we'll look at how to identify if an equation represents a function, the different ways to represent a function, how do we test if it's a function algebraically, and how do we evaluate functions. Okay, so that's our main overview for this video. Now, when we speak of function, many everyday scenarios involve two quantities that are related to each other by some rule of correspondence. In mathematics, or in mathematical term, for such rule, the correspondence is what we call a relationship. So, for example, you can have the relationship between the time of day and the temperature, or you can have the relationship between the money you have in the bank and the amount of interest you earn. So those are examples of some sort of function. Well, let me present you with a definition of a function. So here we can see a function, and the most common notation for a function is f. From a set A to a set B is a relationship to each element x in set A, exactly one element in set B. Okay. In addition, we say the set A is the domain for a set of inputs. So the input is called the domain of the function, and the set B contains the range. So whatever it's mapped to is the range. So if I give you a little picture, here we have a picture of the function. Okay. To understand this definition, look at the function below, which represents the time of the day to the temperature. So notice 1 is mapped onto 9. 2, right, at 2 p.m., we have 13 degrees Celsius. At 4 p.m., it is 15 degrees Celsius. At 3 p.m., it's also 15 degrees Celsius. So here we see that, two different values can be mapped into set B. Yeah. So the ordered pair, if we look at this here, the ordered pair can represent the above picture. So we can have the set 1, 9, and that's because the 1 is mapped into 9. Yeah, let's use a different color for that. 9, and then comma 2 goes to 13. Okay, comma 3 goes to 15, comma 4 also goes to 15, 5 goes to 12, and 6 goes to 10. So the coordinate, the x value, is the input, and the second coordinate, the y value, is the output. Okay. So we could either have it as some form of a pictorial view, or we could have them as ordered pairs. And we'll see later on, we can even have them as a graph. So here we have characteristics of a function from set A to set B. Each element of A, right, every single element in set A must match with an element in B. Okay. Now, it doesn't say that all the elements have to be used. Some elements in B may not be matched with any elements in A. Two or more elements in A may be matched with the same element in B. An element in A cannot, and this is very important, cannot, okay, be matched with two different elements in B. So those are some of the conditions or characteristics of function from A to B. So if we look at a different scenario, okay, or different ways to represent a function, there are many ways a function can be represented, okay? So let's look at some of those ways. 4 ways that we present, right, in which a function can be presented verbally. So we have verbally, then we have numerically, graphically, and algebraically. So those are the 4 ways a function can be presented to you. And we'll look at examples. We will look at examples to see, if not all, but most of them. So let's look at a numerical scenario, okay? This will be numerically. Let's list this numerically. And the idea here is to determine whether the relationship or relation represents y as a function of x. Now be very careful, we're looking at y as a function of x, okay? So what does that mean? It means that the input value, okay, the input value x is the number of representatives. Okay, from a state. So this is what our table here is going to represent. And we can say, and the output value, okay, y is the number of senators. Okay. So if we look at a table for this, a table, let's create some form of a table. So we're going to have here the input, which is the x, and here we have the output, which we call the y. And I could fill in those. We can say that we have 2, okay, and the y value is 11. And we have 2 again, and the y value is 10. And we have 3, 8, 4, 5, and then 5, 1. Okay. So let's call this here A, part A, and let's call this part B. And then part C, if I give you a graph, here's 1, 2, 3. So here's the X, here's the Y, 1, 2, 3, minus 1, minus 2, minus 3, minus 1, minus 2, minus 3. So let's say I put points here. Here's a point, 2, 2, 3 is a point. Here's another point. Here's a point, and minus 2, 3 is also a point. Okay. So let's look at these 3 examples, right? Determine whether the relationship represents y as a function of x. Now, the first one for part A, if we look at this scenario here. So in this example, the input x is the number of representatives from a state, and the output value y is the number of senators. Now, I don't know if you're familiar with senators and representatives per state, but the verbal description, okay, describe y as a function of x, okay, and that's given. So y is a function of x. The input value 2 is matched, okay, the input or the representative, or regardless of the value of x, the value y is 2, okay. It doesn't matter how many representatives we have, okay. It doesn't matter how many representatives we have, but the output value for each state is the same. The output value, okay. So this does not represent a function, because that y value is a constant value, okay. The y value does not change. It's a specific value. Now, if we look at scenario B, here, this is not a function also, because if you notice here, 2 is matched onto 11, and 2 repeats, is also matched onto 10. So we cannot have that repeated value, and that's one of the stuff we said here, right? An element in A cannot be matched with 2 different elements in B. Okay? 2 or more elements in A may be matched with the same element in B. So you could have 2 going to different values, okay? They cannot go, but 2 values, the input, cannot go to different values. So we said here that this table does not describe a function, or y as a function of x. The input 2 is matched with 2 different y values. And you will see later on when we do what is called the vertical line test, this will probably be easier for you to see. Okay, maybe easier for you to see as to why we're saying this. Okay, if we look at C, if we look at scenario C, here we can see that the graph does describe y as a function of f. Each input value is matched with exactly one output value. So this does describe a function y, or describe, let's write that out, describe y as a function of x, right? Each input value is matched with exactly one output value. Yeah, exactly one output value. So, as I said, later on we'll do something where we test graphs to see if they're a function. Now, what happens if we have, or we look at the algebraic way? What happens if we have an algebraic way? So how do we test? Let's look at test. Testing for functions. Okay. Algebraically. So if we have the function, or the goal here first, to do this, we must solve a function for x, for y, okay? This represent y as a function of x if we obtain one output for each input. Let's see what that means. Okay, let's look at an example. So example, okay, determine whether y is a function of x. We want to determine whether y is a function of x. And if we look at example A, we have x squared plus y is equal to 1. So let's solve for y. And we're doing this to see if y is a function of x. Okay. So if we have this, we take x squared plus y equals 1. then we'll minus x squared on both sides. And if we do this, we have that my plus x squared and minus x squared will cancel. Y is equal to 1 minus x squared. Okay? So here we solve for y. Y is isolated. Okay? Now, if you look here, no matter what x value you plug in, okay, there's only one value for y. Okay? So in here, you should notice each x value will produce only one y value. Okay? Every single x value will produce only one y value. Now, if we look at, this was A, at B, let's look at example B. Same direction. Example. How about if we have minus x plus y squared is equal to 1. So we want to solve for y. So minus x plus y squared is equal to 1. Let's solve for y because we want to see if it's a function of x. So what we'll do is add x to both sides. Okay. And if we do this, we notice that the minus x and the plus x will cancel, leaving me with y squared is equal to 1 plus x. Okay. So we have y squared is equal to 1 plus x. And now we take the square root of both sides. And when we do that, we will get plus or minus the square root. So we now have y is equal to plus or minus the square root of 1 plus x. And what you will notice here, so here, just as we did above, right, y is isolated. Yeah. You will notice that, note, for each x value, we will have 2 y values, right? Because of the plus and minus. So if x is 3, right? If x is equal to 3, we have y is equal to plus or minus the square root of 1 plus 3. So y is equal to plus or minus the square root of 4. So y is equal to plus or minus 2. So here we have 2 values. Okay. For every input, we get 2 values of output, 2 exact values, and those, because we have 2 values for input, it's not a function. Okay, so this is not a function. Now, we are accustomed to see functions generally written, or equations generally written as y equals. So because we're speaking of functions now, okay, because we're speaking of function, if we have the equation, so let's say given y, so we're accustomed to give an equation as y equals, and here we know that y is what we call the output, and x is what we call the input. Now, because we're talking about functions now, we want to represent the input, the output as f of x. Okay, and the output will still be, the output is still y, but y is now replacing or being replaced with x, f of x. The input is still x. So the new equation that we'll be working with is f of x is equal to 1 minus x squared. This is where we have function notation. Yeah. So f of x is just the most common letter used, okay? F. The x, when we write f of x, we read this, okay? We read as f is a function of x. This is the way we read it. And basically what it implies on the left side of the equation, there is the variable x. Okay. So if we have f of x equals x squared plus 2, I'm saying because there's an x here, you should expect, and it should be the same x2, okay, not a different x. So these are just a different way of writing things, okay? Now, this helps us in the sense because now we can evaluate, okay? We're able to evaluate a function. At some given input. So, example, let g of x equals minus x squared plus 4x plus 1, okay? And suppose I ask you to find g of 2. So notice we have g of x. G of x is equal to minus x squared plus 4x plus 1. And we're asked for g, okay, g, but now we want 2. We want the x value to be replaced with 2. Now if I replace x with 2 to the left side of that equal sign, I must replace x with 2 every place that I see an x, okay, I have to replace x with 2. So 2 will go in here and 2 will go in there. Okay, that's all I'm doing. I'm replacing every single x value with 2. So g of 2, if we now evaluate this, the minus, and this here becomes parentheses times parentheses. So we have 2 times 2. So this is 4, okay, plus 8 plus 1. So we have minus 4 plus 8 plus 1. So g of 2 is equal to 5. So when, observe what this means. When x equals 2 is put into the function, we get an output of 5. So here 2 is the input, 5 is the output. Yeah, that's what we're looking at. And we can continue. You don't have to just plug in numbers, right? If we look at another example, okay, let h of x equals 2x squared minus 4. Okay. And similarly up here we said find g of 2. So here we can find the output for h of t. Okay. So notice here we have h of x is equal to 2x squared minus 4. Well, now we are replacing x with the letter t. So it means that on the right side, wherever I see x, I will replace it with t. There's no simplification to be done here. So h of t is 2t squared minus 4. And there is our evaluation of when t is plugged into the function. If we look at another example, because no one ever said that we just have to plug in a letter or a number. So let g of x, okay, these are the common letters. Notice I'm using g of x or h of x and f of x, right? We can call this one here f of x. These are just the 3 most common representation of function, f, g, and h. So f of x is equal to, let's say, 2x minus 4. And we want to know, find f of x plus 2. So notice now that instead of f of x, or f of x is given to us, but instead of x, we're not going to plug in, use x anymore. We are now replacing that with x plus 2. Okay, the x is being replaced. So this x is also going to replace with x plus 2. And here we can simplify it. If we simplify this, we have f of x plus 2 is equal to 2x plus 4 minus 4. So f of x plus 2 will be equal to, this will cancel with that. Okay, so we left with 2x. So when the input is x plus 2, the output is 2x. These are just some simple functions that we're evaluating or we're plugging in specific values for our inputs. Now, there's also something that's called a piecewise function. Piecewise. Piecewise functions. And basically, what a piecewise function is just a function that's made up of different pieces of graphs or equations. So a piecewise function, for example, we can have f of x is equal to, we'll have 2 pieces here, x squared plus 1 and x minus 1. And the domain for x squared plus 1 is x less than 0. And the domain for this one here would be x greater than equal to 0. So keep in mind that whenever we have values here, and that's why for less than 0, we will use this function. And when we have values for greater than or equal to 0, we have to use that function. And that's basically what a piecewise function is. So if I ask you to evaluate f of, let's say, 2, then f of 2, okay, f of 2, right? So notice that the input is 2. So we have to use the bottom port, x minus 1. So we'll use the function x minus 1, okay? Because, and let's give that a different name. I don't want to call that f of x, okay? So f of 2, and now we replace this with 2. So f of 2 is equal to 2 minus 1, which is equal to 1. So f of 2 is 1. Now, if I ask you to evaluate f of minus 3, so notice now, note input is minus 3. So f of minus 3, now you have to use the other part of the function because minus 3 is less than 0. If we use minus 3 squared plus 1, which is equal to 9 plus 1. So f of minus 3 is equal to 10. Okay. So be careful for piecewise function. For a piecewise function, be careful as to which piece of the function you use as you evaluate. Be very careful with that. You have to be very careful. Now, we can also talk about the domain of a function, right? Which we have, or I have created a video on domain of function before. So remember, just a quick review on domain of functions. So the domain of a function can be described explicitly or it can be implied by the expression. So the domain, keep in mind, is the domain is the set of all real numbers, is the set of all real numbers, okay, for which the expression is defined. For example, if we have f of x is equal to 1 over x minus 2, okay? So notice the domain exclude x value. So your domain will exclude, so observe the domain will exclude any value that will make denominator 0. Okay? So notice here that if x is 2, okay, if x is equal to 2, this creates a problem. So we must exclude x equals 2. So the domain here, okay, the domain would be every single thing on the number line, every single thing on the number line except 2. So this leaves me with minus infinity 2 union with 2 to infinity. Okay, this is the interval notation. Okay, the interval notation. If we look at another example, okay, find our, let's say g of x is equal to the square root of x. Now, in this case, we know that we cannot take square root of any negative number. So x, therefore, x has to be greater than or equal to 0. So if you look at the number line here for this example, 0 from here going all the way out there will work. So is including 0, because the square root of 0 is 0. So from 0 to infinity, that will be the domain. Okay? And this is interval notation. So you have to be able to look at these functions and identify the domain. Okay? We're not going to look at range at this point, but at least you should be able to identify the domain of the function. Yeah. Now you will notice that if you look at another example of this, let's say g of x is equal to x squared plus 2x. So identify the domain. So you will see that the domain, okay, the domain, so this is a little note here. Note the domain of all polynomial is minus infinity to infinity. And since this is a polynomial, okay, since this is a polynomial here, g of x, so g of x equals x squared plus 2x is a polynomial. Therefore, the domain, so the domain is minus infinity to infinity. And you can see this because any value, right? Any value of x, and when we say any value, all real numbers, okay, will produce or will give an output. So the domain is minus infinity to infinity. So that will be our domain. How about if we look at another example? Um, h of x is equal to the square root of x plus 6. Identify the domain. So here, we should know the square root of negative numbers is not real. So x plus 6 must be greater than or equal to 0, right? And if we minus 6 on both sides, x has to be greater than or equal to negative 6. So on the number line, we have from negative 6 greater than or equal to, everything on this side here will work. So the domain is from negative 6 to infinity. That's our domain. So we want to make sure that we try these things and we put a good effort into observing how do we find the domain. Now, very important for function is something that we call a difference quotient. This is extremely important. The difference quotient. Okay. And this is one of the basic definition in calculus. Use the ratio. Okay. So in calculus, we use this a lot. And the difference quotient is f of x plus h minus f of x, everything over h. So notice since we have a fraction h, okay, h cannot be equal to 0. Okay? This ratio here is what we call the difference quotient. This ratio is a difference quotient. Okay. Now we will see the whole application of this when you take calculus, but for now we just want to present it to you and see how do we use it. And it's a very simple, it's really evaluating functions at some point. So let's look at an example. Let's say given f of x is equal to x squared minus 4x plus 7. And we want to find, okay, f of x plus h minus f of x divided by h. Now, what I like to do is to break this up into parts. So let's look at our solution. F of x is given to us as x squared minus 4x plus 7. And we know that the difference quotient that we have is f of x, f of x plus h minus f of x, everything over h. So notice we have this is really this, but we don't have, we have to find this guy. Okay, we need to find what this is. Okay, So we can find f of x plus h by using f of x is equal to x squared minus 4x plus h. So f of x plus h, what I'm doing is everywhere I see x, I replace it with x plus h. So this is going to be equal to, okay, x plus h squared minus 4 times x plus h plus 7. Everywhere I see an x, I replace it with x plus h. And then we simplify it. So f of x plus h will be equal to, if you simplify this, you'll get x squared plus 2xh minus, if you simplify this, 4x minus 4h plus 7. And if we combine like terms, there is no like terms here, right? And I left out something here. When you simplify this, you get x plus h times x plus h. So this becomes plus h squared minus 4x minus 4h plus 7. Okay? So there is no like term to simplify. So now I can use the difference quotient. So this here is my f of x plus h. So f of x plus h minus f of x over h, we now have, okay, x squared plus 2xh plus h squared minus 4x minus 4h plus 7. And notice this here is the f of x plus h minus my f of x. This here is my f of x, which was x squared minus 4x plus 7. Yeah, everything over h. So if we simplify this now, we have x squared plus 2xh plus h squared minus 4x minus 4h plus 7. And be very careful with that, because a lot of times when you distribute, you get minus x squared plus 4x minus 7. Everything over h. So filling in and canceling out, you will notice that this will cancel with that. Yeah. Also, this will cancel with this. Also, this will cancel with that. So what are we left with? We're left with 2xh plus h squared minus 4h. Everything else cancels, everything over h. Okay? So notice we can factor out h in the top, and that will leave me with 2x plus h minus 4, everything over h. And then notice that this will cancel with this. So we have f of x plus h minus f of x over h is now equal to 2x. Well, let's put that in my blue that I have. 2x plus h minus 4. Okay. And remember, h cannot be equal to 0. Okay. So this is called the difference quotient. Okay. Here we have what is called the difference quotient. So we want to make sure that you become very proficient with the difference quotient. Very proficient. Because this will be used tremendously in calculus. So as always, I close off by saying you need to practice as many examples as possible, okay? And become more familiar with everything that we've gone over, especially to identify when it's a function, when it's not a function, piecewise function, domain, and range. Well, range we didn't talk, but especially domain, and then difference quotient.